So you will have your first exam next Friday. To be on the 4th, 8 a.m. to 8:50 a.m. I will send some of the questions that you might expect in the exam. And I'll work on them over the weekend. So I will send those on Monday. And then we'll review on Wednesday. So it might, if we complete this section 1.4, then it might actually cover up to section 1.4. Or if we finish section 1.5 on Monday, then it will be up to section 1.5. So either I'll let you know on Monday. Okay, let's continue. So we are looking at matrix equation and the linear system. So what is a matrix equation? So let's look at definition 2.1. Definition. A matrix equation is of the form AX equals to B. AX equals to B, where A is an M by N matrix. B is an element of Rm, and X equals to X1, X2, up to Xn. And this X is a vector consisting of n variables, X1, X2, up to Xn. So a matrix equation from Ax equals to B, where A is the M by N matrix, and B the element of Rm, and X is a vector consisting of n variables. A vector S, which is equals to S1, S2, up to Sn in Rn is a solution of Ax equals to B. Ax equals to B. If As equals to B is true. If As equals to B is true. Now, the sets of solutions of the matrix equation Ax equals to B is called the solution sets of Ax equals to B, or the solution set Ax equals to B. So matrix equation of the form A is equal to A is n by n matrix. B is an element of Rm and x equals to x1 with a vector consisting of n variables. Vector S is the solution. Rn and S is the solutions which are S1, S2 up to Sn. So those solutions which are S1, S2 up to S are the same as are equals to the ones which you're getting from here, which are S1, S2 up to Sn. Okay, now let's look at example number 4. Example number 4. Show that the vector x equals to -1, 0, and 1 is a solution of the following matrix equation. Show that the vector x equals to -1 is a solution of the following matrix equation. Okay, so if we have this equation, 1, 2, 3, 2, 3, 4, and then we have the vector x, x1, x2, x3, which is equals to 2 and 2. So this is the matrix equation, and this is the matrix A. This is the vector x, and this one is B. So the matrix A is a 2 by 3 matrix, and this is a 1 or n by 1. And then this one is also, this one is a 3 by 1, and then this one is a 2 by 1. So that's a 2 by 1. So if you look at this matrix, so if you look at this one is an element of what? R2. So we have 2 entries there. As we can see from this definition here, the vector B or B here is an element of M, and this M are the number of rows which are there, or the number of entries. So in this case, this is an M, and this one is an N. So that is an M, and that is an N. So show that this vector X, which is now X1, X2, and X3, is a solution of that. So how can we show that? So the solution. Now, when X1 equals to -1, X2 equals to 0, and X3 equals to 1, then 1, 2, 3, 2, 3, 4 is now similar to X1, X2, X3 equals to 1, 2, 3, 2, 3, 4 multiplied by -1, 0, and 1 there, which is the same as using the row vector rule. Then this is equals to 1 multiplied by -1 plus 2 multiplied by 0 plus 3 multiplied by 1. And then the next one is 2 multiplied by -1 plus 3 multiplied by 0 plus 4 multiplied by 1. And this should be equals to, so this should be equals to, this is -1 but this is actually 0, plus 0, and then plus 3. And then the next one is -2, plus 0, plus 4. And finally, this is equals to 2 and what? And 2. This is equals to 2 and 2. So it means that this is now the solution set for the following matrix equation. Any question? Okay, example number 5. Okay, you can still follow this one. I'll send the video in YouTube, so you can in Moodle, so you can look at it. Okay, let's look at example number 5. Convert the following linear system to an equivalent matrix equation. We have the linear system 8x1 minus x2 equals to 4, 5x1 plus 4x2 equals to 1, and then x1 minus 3x2 equals to 2. We have such linear system. So how can we convert this one to equivalent matrix equation? So let's look at this. So we want to convert this into the form AX equals to B. AX equals to B. So how would we convert that? So first, we convert the linear system to equivalent vector equation. So let's convert this one to equivalent vector equation. And how did we do this? So what we did is we now take now 8x1, 5x1, x1, put it there, and then plus minus x2, 4x2 minus 3x2, like that, equals to 4, 1, and 2. Equals 4, 2. And then we factor out the common variable there. In this case, x1 here will now be 8, 5, and 1. And then plus x2, now it will be -1, 4, and -3 equals to 4, 1, and 2. Equals to 4, 1, and 2. So that is the equivalent vector equation. Now, we now take the vectors there. So this is like vector A1. And this is like vector A2. And this is like now the B there. So we know that the matrix is, let's say matrix A is the same as vectors A1 and what? A2. A1 and A2. So we always so vectors. So in this case now, we now form now the matrix, which is this A, which is now the same as the collection of those vectors, which is 8, 5, and 1. and then -1, 4, and -3. And then our x will now be, our x here is the same as x1 and 1, x2. So x is x1, x2 there. Then our b equals to 4, 1, and 2. 4, 1, and 2. So that is our matrix image. So that's how we can do it. So make sure you consider the size. This negative and that. So make sure you don't. Okay, now let's look at example number 6. Convert the following matrix equation to equivalent linear system. Now, if we have the matrix equation of this form, 4, -4, -3, 5, and 3, -2, 5, 4, and 0. And then x1, x2, x3, x4 equals to 4 and 13. So how would we convert that into equivalent linear system? Into equivalent linear system. So if we use the raw vector rule, so that is where we multiply this and that, this and this equals to this and this, like that. So this solution by use of raw vector rule, we get 4x1 minus 4x2 minus 5x3 plus 3x4 equals to 4. Then minus 2x1 plus 5x2 plus 4x3 equals to plus 0x4 equals to 13. So that is how we get linear system. So that is the linear system. It is the linear system. So let's look at the remark. And this remark is the augmented matrix associated with the matrix equation AX equals to B is A and then B. X and then B. So the augmented matrix associated with matrix equation is A. So this is fine. So it means this can be now a coefficient matrix, and then we now add this B here. Then it becomes what? It becomes the augmented matrix. Any question? Any question? Of course, it's easy, right? It's very hard. Yeah, this section I think chapter 1 is easier than maybe chapter 2 and the rest. So exam 1 can be very easy. So I am expecting each one of you to get 100%. Okay. Now let's look at another example. Example number 7. Now let's solve the following matrix equation. Solve the following matrix. Now we want to get the solution. The solution vector, which is S. So if we have the matrix equation 1, 2, 1, -3, -1, and 2, 0, 5, and 3, x1, x2, x3 equals to 0, 1, -1. So solve that. So we want to get the solution. That means we want to get the values of x1, x2, and x3. X1, x2. So how can we solve this? So solution. So using the previous plank, we say you can write this in words. Matrix form, and then we do we reduce the matrix. We reduce the matrix completely. So we use a reduce, we reduce it to the row echelon form. Use the row echelon form. So writing this in augmented matrix, so 1, 2, 1, then 0, -3, -1, 2, and then 1, 0, 5, 3, and then -1. So now reducing that matrix. So we have to reduce this, and then also want to make dots which are about the leading entry to be zeros. Actually on the table. So let's first of all we want to reduce this. So to reduce this one, we want to see whether it is consistent. That means for it to be consistent, then the last row here should not be contradictory. Now, if it is not consistent, then we will not, the solution there will be what? Undefined. So let's start by reducing. So again, you make sure this first entry here is not 0. So if it is 0, then you switch the rows. But here it is not 0. So we want to reduce this. So our new R2 will be our R2 plus 3 R1. R2 plus 3 R1. So our first row there, and then this will now be 0 minus -1 plus 2 is 5. 2 plus 3 is 5, and then 1 plus 0 is 1. This one still remains the same, 3, and then -1. Then we now make this one 0, so it will be the new R3 will now be R3 minus R2. R3 minus R2, 1, 2, 1, 0, 0, 5, 5, and 1. And then this will be 0. This will be 0. 3 minus 5 is minus 2. and then -1 minus 1 is -2. Next. So we have the pivot positions there. So each of the columns, we have the pivot position here, here, and here. So therefore, this is not what. Yes, because this is not. Now, so we now want to make these ones to be 0 and this one to be 0, and also this one to be what? Be 0. So before we make that one to be 0, we need to make this one to be what? 1. So our new R3 will now be multiplied by -1/2 R3. So what do we get? So we get 1, 2, 1, 0, 0, 5, 5, and 1, and then 0, 0, 1, 1. 0, 0, 1. Any question up to that? Okay, now we want to make this one 0 and this one 0. So to make this one 0, then it is our new R1 will be R1 minus R3. R1 minus R3. To make this one 0, then our new R2 will be R2 minus 5 R3. Minus 5 R3. So let's start from the first one here. So R1 is R1 minus R3. So this is 1 minus 0 is 1, 2 minus 0 is 2, 1 minus 0 is 0, and then 0 minus 1 is -1. And then R2, our new R2 is R2 minus 5 R1. So 0, 5 minus 0 is 0. 5 minus 5 is 0. Sorry, this is 5. And then 1 minus 5 is -4. Then this is 0, 0, 1, and then 1. Also, we now want to make this one to be what? 1. We want to make this to be 1. So we said the reduce H log 4, all the leading entries should be 1. Should be 1. So the new R2 there will now be, we multiply 1/5 by what? R2. So it will be 1, 2, 0, -1, 0, 1, and then 0, then -4/5. So this is 0, 0, 1, and 1. So we want to make this one to be 0. So our new R1 should now be R1 minus 2 R2. R1 minus 2 R2. So finally, what do you get? 1. So 1. 2 minus 2 is 0. 0 minus 0 is 0. And then -1. So -1 here, right? So -1. Now plus what? Plus 8/5. Plus 8/5. So what do you get? 3/5. 3/5. So we get 3/5. And then finally, this will be 0, 1, 0, and then -4, followed by 5, 0, 0, 0. Sorry, 1, and then 1. Okay, now to write this one back as a linear system, then what do you get? So we get x1 equals to 3 over 5, x2 equals to -4 over 5, and then x3 equals to 1. So therefore, the solution set is x1 equals to 3 over 5, x2 equals to -4 over 5, and x3 equals to 1. x3 equals to 1. Any question after that? So you should expect something that is. Okay, now let's come to the next section, which is 3 in this section 1.4, and this one is vector spanning and vectors spanning. So let's look at definition 3.1. Definition. So if we let vector 1, v1, v2, up to vp be vectors in Rn. We say that vectors v1, v2, up to vp span Rn if every vector b in Rn can be expressible as a linear combination of v1 up to vp, namely the vector equation x1 v1 plus x2 v2 plus xp vp equals to b. So if the vectors is a linear, if you have this vector, so these vectors on Rn, if every vector b in Rn can be expressible as a linear combination. I mean, look at what we meant by the linear combination. So the vector equation is of this form. So that means for this one to be linear, for this to be spanned out, then it means this solution set, this here, to be equal to now is consistent. Is consistent for every b element of Rn, or every b element. Now it should be consistent for this to span. R F should be consistent. So to check whether this is consistent, then we now take these vectors here, all those vectors there, and then we and this vector here, and then we put them in the augmented matrix form, and then we reduce them. Once we reduce and there is no contradictory law, then it means it is consistent. Now, if it is consistent, then it means B spans V1 and V. B spans V1 and VP. Okay, example number 8. Let's look at example number 8. Do the columns of the matrix A equals to 5, 8, 7, 0, 1, negative 1, 1, 3, 0. Span and 3. The columns span are 3. So we want to see whether the columns span are 3. So in that case, for this to span, then it means that so the solution. So it means that we are actually looking for x1 v1 plus x2 v2 plus x3 v3, which is equals to what? Which is equals to. So for that to span R3, then therefore, what we do is we now write, so it should span R3, and this R3 are now the elements which are B, which are equals to B1, B2, and what? B3. B1, B2, and B3. So here now, we write this in augmented matrix form, and then we reduce it. So it is 5, 8, 7, 0, 1, negative 1, and then 1, 3, 0. And then now we put this B here, B1, B2, and then B3. B1, B2. Then we go up, then we reduce it. When we reduce it. So to reduce this, then to get the new R3 there, so it is R3 minus 5 R1. Sorry. So what we can do here is, before we do this, so we can switch. So we can switch R3, R1, R3. We can switch R1, R3. We can switch R1, R3. So when we switch that, we get 1, 3, 0, and then B3. So 0, 1, negative 1, B2, and then 5, 8, 7, and then B1. So we are trying to make it easier to solve. So once we switch, then now we are able to reduce. So to get the new R3, then R3 minus 5 R1. R3 minus 5 R1. So what do we get? So what we get here is, so it's here. So we get 0, what am I doing? So 1, 3, 0, B3, 0, 1, -1, B2, and then so this is 0. And then this is -7. And then that is 7. And then B1 -5, B3. B1 -5, B3. Okay, again, we want to reduce this. So our new R3 will now be R3 plus 7, R2. So what do you get? So 1, 3, 0, B3, 0, 1, -1, B2. And then finally we get 0. This is 0. And then this is also 0. And then this will now be B1 -5, B3 plus 7, B2 plus 7, B2 plus 7, B2. So that is what. Now, if you look at this, now for this to be consistent, then it means that this should be what? This should be for this to be consistent. That should be 0. So therefore, we can say the matrix equation AX equals to B is consistent if and only if B1 -5 B3 plus 7 B2 equals to 0. Equals to 0. However, B1 plus 7 B2 minus 5 B3 equals to 0 is not always true for every B equals to B1, B2, B3 element of R3. So it is not always true. So it's not always true for this file. Therefore, the columns of A do not span R3. Therefore, so it cannot be true when this one, because you cannot say when B1 is 0, then B2 can be 0 and B3 can be 0. Not always be true. Okay, let's look at another example. Example number 9. Do the columns of the matrix (1, -3, -4, -3, 2, and 5, 5, -1, -8 span R3? Span R3. So when you go home, this is similar to what we did here. So you use the same way. So what you do is you now introduce another a vector B, which is equals to B1, B2, and B3. And this is an element of R3, element of R3. Once you introduce that, then you write this in augmented matrix form, which is of that form: 1, -3, -4, -3, 2, 5, 5, -1, -8, B1, B2, and B3. So once you reduce this one, then what you get is 1, -3, -4, B1, 0, -7, -7, 3, B1 plus B2, and then 0, 0, -2, B1 plus 2, B2 plus B3 plus B3. So that is what you want to use this special form, then you will get that. Now, looking at this is basically consistent. So this is basically consistent. So therefore, we can say, since matrix since matrix AX equals to B is always consistent for every B, which is an element of R3, then columns of A span R3. The columns of A span R3. Okay, now let's look at some summary here, which you can say this is 3.2. Now, if you look at in example 8, the matrix A has been reduced to an echelon form matrix of the form 1, 3, 0, and then 0, 1, -1, and then 0, 0, 0. Where there is no pivot positive in the third row. And in example 9, the matrix A has been reduced to 1, -3, -4, 0, -7, -7, and then 0, 0, -2. And we can see that there are where there is a pivot position in every row. So therefore, you can see some of the different. We have various position in two of them. Position each one of them. Okay, that is it for. Okay, so all the best. Make sure you submit your homework before 2 p.m. See you on Monday.